Okay, well, thanks for having me. I've taken something from each of these talks so far, and I'm particularly delighted that Anab sort of introduced the session with an insect-based theme, which is something I'd like to develop in my little talk here. So I want to talk about ant now, specifically how we can use swarm intelligence to begin to do the sorts of things that I think several people have been getting at already, which is harnessing messy biological self-organizing processes for the purposes of building things, for designing stuff. And I just want to give you some insights into ongoing research in my group down the road at MMU. So I was reading an in-flight magazine the other day, and it was a really naff article, but it was one of these management empowering sort of management training articles. Why I was reading it, I don't know, but I came across this quotation from Vincent van Gogh, which I thought applied quite nicely to what we're doing. So basically he said, great things are done by a series of small things brought together. Now I'm pretty sure he wasn't talking about ants, but it seems to capture in a single quotation what we're trying to get at, the idea of bringing lots of very small, simple things together to do really great things. And we're all familiar with the notion of a superorganism, the idea that you can have a large number of very simple organisms that behaves according to very different rules. If you take the individuals and put them in a group, suddenly they act like a larger organism. And the obvious example is the ant colony that I'll talk about later, but we've got things like bee colonies and so on. But I want to talk about ants not just as superorganisms, but as supercomputers. So my argument is that colonies of social insects can be considered as biological supercomputers. And not just social insects, we also do a lot of work on using bacteria, which I'll come to later. So the arguments that I'm going to put forward in this short talk are that we can learn from the behavior of social insects, for example. They can teach us how to build. They can teach us how to construct artifacts in our world, and that they can make an impact on our world. So the argument I'm making is that I'm trying to support this assertion that ant colonies can be thought of as biological supercomputers. And individual ants are very simple creatures. At one level, we can look at them in terms of simple machines. They move around, they sense chemicals in their environment, they talk to each other, but they're very robotic almost in their behavior. It's only when you get lots of ants together do you actually get any interesting behavior. So it's the collective nature of the colony that gives it its real power. Now, if you consider an individual neuron as a sort of chemical switch, not particularly smart individually, but you put billions of them together, you create an entity that's capable of writing keynote presentations, producing poetry, and having fights in the street on a Saturday night. Okay, that's not intelligent behavior, but you get my point. You get billions of very simple entities together in a population, you suddenly get consciousness and creativity. And later on in my talk, I want to show you a very simple example of how creativity almost emerges spontaneously from lots of simple things doing very simple actions. So the first example I want to use is termites. So termites, you give them a job piling wood chips. So you scatter a load of wood chips across the surface, and then you have termites, the job being to pile the wood chips into a number of piles. And if we program our termites to walk around randomly, and you give them this basic behavior, if I hit a wood chip and I'm not carrying anything, then I pick up the wood chip. If I'm carrying a wood chip and I hit another wood chip, drop the wood chip, okay? That's the sort of really simple rule that you can build into, that can be handled by the very small brain of a termite. So if we look at a movie of these things in action, so brown termites are carrying a wood chip, and white termites are just walking around looking for stuff. It's a bit of a choppy movie, but hopefully you can see that structures beginning to spontaneously emerge in this simulation, and you can see how the piles are gradually beginning to form purely as an emergent property of these very simple rules that we've programmed into our termites. And one termite on its own would never give rise to this behavior. It's only when you have hundreds of termites moving around do you get this distributed computation. And the rules were very straightforward. Okay, so we can learn from these creatures. And this is a plaster cast of an ant colony. Bert Hurldubler, who's a very famous ant scientist, basically says that an ant colony is a problem-solving instrument. We can use the behavior of ant colonies to solve problems, okay? The interaction of millions of ants reacting to different stimuli, reacting to each other, okay, can give rise to incredibly intricate structures like the ones we see here. But how? How do we actually use the behavior of ants? We can't actually take a load of ants and plug them into some sort of ant-based coprocessor attached to our laptop, okay? We have to build abstract models of their behavior, which we then apply algorithmically to the solution of problems. And we're very familiar with this sort of process. We've abstracted evolution to build genetic algorithms. We've abstracted the behavior of the brain to build neural networks, okay, to do pattern recognition. So ant-based algorithms have been very good at solving problems, for example, routing. Now, how can we route mobile phone traffic, for example, using the behavior of ants? Well, we harness a property of these natural systems known as stigmergy, which allows indirect coordination between collections of agents. So we allow agents to somehow modify their environment, maybe by laying a chemical trail or something, okay? And this gives rise to self-reinforcing, self-organizing processes, which in turn give rise to the emergence of unplanned yet coherent behavior. So these things can... Okay, so here's a simple problem. We've got a load of ants in their colony to the left, and they want to get to the cake on the right. Unfortunately, there's a big elephant for some reason in the way. So there are basically two routes these ants can take. And we're often very interested in, if you've ever used Google Maps to get directions, you want the shortest path from A to B. This is how we can use stigmergy to automatically find the shortest path from A to B very quickly. So we set off these ants, and they're walking, and they're walking. Okay, so the one at the bottom, because it's a slightly shorter route, gets to the cake first. And when it's carrying food, it starts laying a food trail, saying, I've got food, on its way back to the nest. So its mate is way behind. So the next time you have an ant emerging from the nest, it's looking for a scent. So it picks up the scent that's already been laid by the guy that's come, sorry, the girl that's just come back with the food, okay, and then very quickly you get this reinforcing of the shortest path without anybody actually saying food over there, take a left at the twig, straight on, and then right at the dead bee, and there you are, okay? Nobody says any of that. It's simply very simple rules giving rise to very quickly emergence of the shortest path. Now, that's been used very successfully to route mobile phone traffic, okay? To schedule vehicle deliveries, loads of different problems on networks, okay, that involve finding a path from A to B via C. In our group, we were very interested in how we can actually create two-dimensional structures using these behaviors. So we define the rules and let the structures self-organize, let the structures emerge. So we're interested in how we can achieve structures without having any sort of top-down placement of components. And the problem that we want to solve is, given a collection of objects, small, medium, and large, how do we create a sort of bullseye structure? Okay, so this might be the sort of thing, if you're programming a swarm of robots on the surface of Mars, you want to get samples of rocks and pile them up in a certain way. Okay, how do you actually achieve this self-organization? Okay, so this is actually inspired by the way that ants tend their nests, with the smaller eggs at the center in a core, and the larger objects, sort of the more ripe objects, on the outside. Okay, so we have a simple mechanism where we have a balance between attraction and repulsion, where we build a shell around each object. So each object has an attractive shell, the green shell, and a repulsive shell, the red shell. So each object wants to have a certain number of objects in its immediate environment, so you get coherence, but it doesn't want to be too crowded, okay? And the size of each shell is a function of the size of the object. So the ants move around randomly, basically picking up objects, and if they're carrying an object, they look at the local attraction repulsion and decide whether or not they should drop the object. And if it's okay, they drop it. So this is very similar to the behavior of the termites. And this gives rise to what we may call the muesli effect, where if you shake a packet of muesli, you get the larger flakes sort of rising to the top, and then what you're left with at the end is basically mouthfuls of dust, okay? And that's the same sort of process. So here's the ants in action doing their sorting. So we start off with an early exploration phase, where the ants are just moving around and running around and picking things up and dropping them down. But you can see there's not a lot of structure yet. And then we move into the second phase, which it's a very technical term that we use, faffing about, where they spend a lot of time, they've got a rough structure, and then they spend a lot of time running around faffing about, just basically picking things up and putting them back down again. So here you can see we've got the beginning of the structure emerging with the core of small objects in the middle, and then a sort of ring of medium-sized objects around that, and then larger objects around the outside. And when you're watching the simulation, you find yourself going, "No, don't pick that one up. That one was fine where it was. Pick that one up. Get that." They can't hear you. They're artificial ants. And then at the end, you've got final refinements where they run around nibbling the structure. Okay, so these sort of results that we get. But then we thought, well, what happens if we actually make the job a bit harder and actually start with three, rather than randomly distributing all the objects, start with three piles. And so basically on the left we have three piles of a small, medium, and large pile. And they have to create the structure on the right, which is, the core of small objects followed by a ring of medium and then an outer ring of large. And what we found was that they would spontaneously, without any change to the simulation, any change in the rules, any change in the parameters, anything, they would spontaneously form two intermediate sort of working piles. Okay, so they would take the three starting piles, merge them into two working piles, and then one of the working piles would gradually be sort of evaporated and sort of integrated with one of the others, with the other pile, and then that pile would be sorted. And that was a sort of creative process, a creative solution to a problem that spontaneously emerged. We didn't actually build that in. We didn't tell the ants to build a working set of piles. Okay? They did that all by themselves. So I would argue quite, well, not strongly, but this is a form of creativity. Okay, so we're familiar with termites, and these are some of the structures that termites, some of them looking very cathedral-like, some of them very large. Okay, and these are the sorts of structures that have been built by large colonies of insects. So in our group, I'll just finish with this, in our group we're interested not just in termites, but in bacteria. And we use living bacteria to build computers. And we're very interested, these are all spatial patterns that have been generated by groups of bacteria basically trying to solve problems in their environment. So they're trying to look for food, but moving costs, okay? Costs a lot of energy to move around, so you're doing constrained satisfaction. You're trying to work out the best way of doing X and Y whilst avoiding doing Z. So these are all pictures of bacterial colonies that are solving a problem in their environment. So basically, in our group, we're interested in using these bio-inspired self-organizing processes to design urban systems. And my PhD student, Danny Richards, is specifically interested in asking these questions. And he's really driving this research. So he's basically asking the questions, how do we construct complex spatial structures using these simple encoded processes? And can biological processes, such as the ones we've seen, and the processes that occur between living cells, for example, can they suggest new ways, new methods of building urban systems and constructing new forms? And how would we actually assess the value of what we produce? And that's a very tricky question. How do we actually assess the goodness of an object that's produced by such complex phenomena arising from simple behavior? So I guess I've posed more questions than I've answered. But I'd just like to close by with some acknowledgements. The ant clustering work was done with my student Oliver Don. Danny, who's my current PhD student, has really driven the thinking on architecture and urban systems. And a mandatory acknowledgement goes to the university, the EPSRC, and the European Commission for actually paying for my group to exist. So thanks for listening.
Yep. Hi, Martyn. I'm just wondering how the bacterial kind of pattern making and the ant intersects with this idea of synthetic biology.
Okay, well, that's one of the other. I know Anna mentioned synthetic biology earlier, so if anybody's not familiar with synthetic biology, it's the notion of engineering living organisms to get them to do cool, wacky, non-standard things. So getting rabbits to glow in UV light and so on. We do some of that work in our group as well. I mean, we're interested in engineering bacteria to basically do line dancing. We want to do bacteria that can, you throw them in a dish and you don't say, okay, you go here, you go here, you go here. When we originally started putting the funding proposals together, we were going to get, it was when London was trying to get the Olympics. So we were putting lots of pictures of bacteria sort of spontaneously forming the Olympic rings. From an initial sort of colony, they would all run out and do basic bacterial line dancing. We didn't put that in the proposal, though, to form the Olympic rings. And from the synthetic biology point of view, we're interested in engineering cells that will self-organize into specific spatial structures, because it may well be that if you can persuade cells to adopt very specific three-dimensional structures, they can then, for example, deposit a calcification agent or something to form three-dimensional scaffolding, which can then form the basis of artificial tissues, for example. So it's very, very early days. We're still playing around in the sand with this stuff, but I mean, the eventual aim is to engineer bacteria, engineer cells, maybe even human cells, to adopt complex three-dimensional shapes for functional purposes. Yeah.